square root of that is, right? That'll work. We really make the connection when we see these applets again. So I wanted you to see this. That color, it is green, right? Is that green? Okay. That green's going in the same direction as the gradient vector. What's the directional derivative value right there? 2. But if I swing this direction another way, it's going to do the dot product and get, but watch, it won't be this high. The highest value, the highest rate of change occurs when the directional vector is in the same direction as the gradient vector. That's that cosine of 0 degrees, being 1. The maximum value of cosine. 0 degrees between the vector. So I'm just going to slide it a little bit. What happens to that DUF? Does it go down? Yeah, let's go this way. Yeah, is it going down? Yep. When can I get the highest of this number right here? I'm just move my mouse around it. When can I get the highest value here? When that vector is in the same direction as the gradient vector. I just want you to see that so you know why are we answering this. We're saying that the direction that provided the max rate of change is the direction of the gradient vector. Cool. Awesome. Hey, so on that note, you all have the hill problem? I'll pop that up here. Let's do that. It's going to be very similar, but it's kind of cool. It's slightly different. I just want to make sure we work this together. So I'll keep this up here, and I'm just going to pull open. Let's see. I need to. Where's the hill? There it is. Pull that up. That'll work. So when we're standing at that blue point, everyone see that equation? 1,000 minus 0.005 x squared minus 0.01 y squared represents that graph. I made that graph with blend plot. I didn't show the whole graph. I just made sure that I wanted to zoom in on this gigantic hill. Zoom in on this hill, by the way, right there, that x-intercept would be at z equal to 1,000, right? Because x, y would equal 0. So I'm taking this point right here, and that's the point 60, 49, 66. Cool. So we're standing on that point blue, and we're going to talk about, directional derivatives. I mean, you all can tell that when if I go in that direction, won't my slope be positive? But if I go in this direction off the point, it'll be what? Negative? Maybe I kind of go like that. Maybe there's a way I can get the slope to be 0. That's in some direction. Well, let's go through the questions. Won't take long. So I'll swing this down. Letter A, the question is, if you walk due south, will you start to ascend or descend? Let me pull this out again. If you walk due south, so let me erase all this. If you walk due south, this is out of the way. What was z again?
1,000.
I mean, the equation. F of x, y. What was the function of x and y? 1,000 minus, just so I can leave it on the board, 1,000 minus 0.005 x squared minus 0.01 y squared. So it is an upside down paraboloid, right? I just took that certain portion. Letter A, they asked me about some directional derivative. Let me pull it back down again. If you walk due south, will you start to ascend or descend? And they said at what rate? So, but see the directions for north and south? So we're talking about, see that's the xy axis? Now I can just draw it right here. In terms of x-axis, y-axis, and when this is north, and this is south, this is east, and this is west. So the hardest part to letter A, I'm going to do a directional derivative problem because they want us to find a rate. Everyone agree? I need to find a rate. But why I had to do this problem? We just did a problem. You're like, I'll be fine with this. No, we got to do this problem as well because something tricky about this problem. They never gave you the directional derivative. I mean, they never gave you the directional vector. They just said what? Due south. So you got to help me out. I know you can do this. Can you tell me a vector, everyone? In my image right here, that points due south, and it's got to be a unit vector.
0.
You got it. That's 0 now. So in the vector we're going to use, when we do this, we go, hey, fx, fy, we'll put that in right here, dot, the vector we're going to use is 0, -1, due south. Notice it's a unit vector, but we're saying it could be a vector with a length of 1 that way. Cool, is that all right with that? What would due north be?
1.
0, 1. What would due east be? 1, 0. What would due west be? Negative 1, 0. Does anyone get that? Just so this problem, there you go. Now there's one other weird one. How would you do like northeast? Can you help me figure that out? I'll try that. Northeast would be a vector that went like this. In case the problem after that. That would be a vector that went like what? 1, 1? Moved 1 this way and 1 that way? The only problem is that's not a unit vector. How can you make that a unit vector?
Divide by square root.
There you go. So there you go. So if they ever ask you like, hey, can you go northeast or something? You go, oh, okay, I'll just 1 over root 2, 1 over root 2. If it's like, you know, going northwest, you might need a negative on one of those. You got it. But right now, we're just going due south. What goes here? This is called the gradient. What's with respect to x?
Points.
Negative point
1,
0, 1,
0x.
0x. Will that work? Negative point 0, 1x. What's fy? Negative 0.02y.
Yep.
And what point was it again? They give us the point. What was the point? Point was, and I'll scroll that up so you can see it. What was the point that we're evaluating this on this hill? We're way up at 60, 40, 966. Well, we don't have to plug the 966 in, but the x was 60, the y, 40. So I'll just plug that in here. So what do we get? So this is directional derivative at the point 60 comma 40. And I get negative, what's 0.01 times 60?
0.06.
Is that
No,
negative
no,
6?
0.6. Negative.
Negative 0.01 times 60, you have to move it how many places?
2.
So I get negative
0.0.
9.6?
Six,
And
yeah.
what's negative 0.02 times a 40? Is that negative 0.8?
Uh-huh.
Alright, cool. They said find the rate. What else did they ask? They want us to know if we ascend or descend. Well, obviously, the answer is positive or what?
Ascend.
Going uphill, ascending? It's negative, we'll go downhill. What's the answer? 0.8?
Yeah.
And I'm going to write 0.8 if you want to know units. Vertical meters, everything was in meters. 0.8 vertical meters per 1 horizontal meter. Right? But I'm going to put ascend. Cool. Awesome. Hey, B asks you to go northwest, you do something similar. You know, they go northwest, just for northwest. What unit vector would you use? For northwest? Yikes, what would be a vector that goes like that?
Oh,
Vector, what's your directional vector?
negative
Negative
1.
1.
Yep.
But then you gotta make it a unit vector, what would you use?
Root 2.
Cool. Was everyone okay with letter A? Alright, letter B. Same stuff, but they go not due south, but northwest. So I'll put it right here. Negative 1 over root 2. 1 over root 2. I'm just curious, do we ascend or descend? What do you get? I get 0.6 over root 2 minus 0.8 over root 2. Negative
Negative.
0.2 over root 2 vertical meters per horizontal meter, ascending or descending?
Descending.
Descending. Hey, I'm gonna go back to the image, just, can you tell which way it went? I'm just telling. Where would northwest be? Let me pull this down just slightly right there. It's good. Can you tell everyone? I'll hop up on this chair. But if you went down, you know you're going in that direction, right? There's northwest. If you're going that way, it looks like you're slightly descending. Cool. That's why I wanted you to see the image. So you can actually relate to the actual image. Rather than us just doing this problem totally blind. Cool. Hey, what's the next question? Oh, we knew this was coming. In which direction is the slope the largest? Which vector?
It's a 0.6, 0.8.
The gradient vector, right? There's two vectors on the board right now. In which direction at that point is the slope the largest?
Negative 0.6.
So the direction where the slope is the largest, negative 0.6 and 8.8, the gradient vector, it's always the direction of the gradient vector. And then they go, what is the rate of ascent in that direction? How can we do that? Let's get the magnitude of the gradient vector. So when this is letter C, it'd be in this direction, this would be for max rate, and that's the direction, but what is the max rate? Well, maximum rate is what? Are you kidding me? He's right. Now, what's negative 0.6 squared plus 0.8 squared?
1.
Right? So what we're saying would be 1 vertical meter per 1 horizontal meter. That would be the max rate of change at that point. Go up 1 for 1 going that way. Cool. Hey, one more thing before we do something else. They did say at what angle does the horizontal, at what angle above the horizontal does the path in that direction begin for this? You know what we'll have to do? Can you help me out with this? All right, we want max rate of change. We can tell it's just going uphill there, right? Max rate of change will be 1 vertical meter per 1 horizontal meter. 1 vertical meter per 1 horizontal meter. So if you don't mind, I'm just going to draw a picture of a triangle there. 1 vertical meter per 1 horizontal meter. Does anybody know how you can get that angle?
45 degrees.
Yeah, inverse tan, I love it. Inverse tan of 1. What is it, 40 what? Is that 45 degrees? Some of you knew it in your head. A 45-degree angle makes this 1-to-1 ratio there. Where this is 1 and that's 1. So the answer to that question there, when letter C is 45 degrees. The question again was, at what angle above the horizontal does it path in that direction again? 45 degrees. Cool? Hey, I'll turn this off. Great job with that, everyone. Man, that was awesome. Any questions on that stuff? That's directional derivatives. Everyone understand the gradient vector too? So cool things about the gradient vector. The gradient vector, I know I got it summarized here, but this is just for your notes. I'll erase them and leave this up here. It provides the direction of the what? The max rate of change. It's always perpendicular at the point of tangency. It always points in the direction of increasing k-values. And it also is very helpful in finding the maximum rate, maximum value of that direction, or the maximum rate of change, which is the magnitude of the gradient vector. Cool. I love it. All right. Hey, I'm looking at your practice set. I just want to make sure there's nothing that was missed. Oh, good. We did a problem like number 17. And with number 18, you see the vectors in there? You got to figure out which one's the gradient vector. I think you'll be okay with that, right? Just be careful. It points in which direction? In direction of the increasing k values. Good. Because I see A and C, and you need to determine whether it's A or C. Cool. 19, they do the, if the gradient of f is this, then the fastest rate of change of f at the origin is given by, don't you just get the magnitude of that? Nice. And number 20, they want the maximum directional derivative. So once again, all you got to do is what? The magnitude of the gradient vector. Cool. But problems where you had to kind of work it out and find a directional derivative, you had to do that in number 16. Cool. I'm looking to see if there's any other ones. Oh, one more thing before we work on, we wrap up class with 14.7. There's one more thing. This gradient vector is so cool. We now have another way to get the equation of a tangent point. So here's another way to get the equation of a tangent point. So this is called, because we did equation of tangent plane in the last section, right? Everyone agree? So you'll see this. I want to tell you what page I wrote this on. This is at the bottom of page 940. This is another equation. For the equation of tangent plane, I will put in parentheses, to level surface f of x comma y comma z equal to k. Here it is. plus Fy. We're a little lower so we can see it. Do you notice what I'm doing? What am I using as the coefficients? Do you remember, everyone, when you had a plane, which vector was the vector we always used to get an equation of a tangent plane? We always used the normal vector. Well, we just said that this vector is always what? Perpendicular at the point of tangency. So guess what we can do? As our coefficients to be x minus the x naught, ef y minus the y naught, ef z minus z naught. We can use the components of the gradient vector, and that's another way to get the equation of a tangent plane. So you might be sitting there going, I don't need that. I did okay in the other section. And when this is listed on page 940, if you're curious, if you want to read about it, where they wrote that, but they're talking about, this should make sense, right? This vector would be what? You know, fx, fy, fz. The normal vector. The gradient vector. But we do say to level surface. We'll say level surface like some function of x, y, and z equal to some k value. Cool. So let's work one like that. So this is like, hey, from your practice problems, this was, if you want to reference it, everyone, look at number 14 and look at number 15. Bless you. And we'll work problems like that. So I'm going to take this one from the textbook. And when